Thank you for attending my talk. Hi, I'm Shravan Srinivasan. I work on applied cryptography at Lagrange Labs. Today, I'm super excited to talk to you folks about verifiable ML inference. The, it's called as DeepProof, and it's a joint work with some of my amazing colleagues from Lagrange Labs. Chris, Zach, Nicholas Menardi, Nicholas Dimitris, and Babis Papamato. So let me begin with a brief big picture motivation. So AI systems have become really ubiquitous in everyday life, ranging from refrigeration systems all the way to autonomous cars and defense systems and so on. However, despite its pervasive usage, these models suffer something called as a trust issue. What I mean by that is, how do I know that the models with which I'm interacting are explainable, robust, and fair? So machine learning community has been trying to solve this problem for a while. Even if they manage to solve these problems, we are still left with a few problems from the cryptography standpoint. That is the verifiability and the privacy problem. So what I particularly mean by this is, how do I know that the result from a non-trusted server is indeed correct? And how can I make sure that as a model owner, whenever I'm trying to prove to you that my results are correct, I do not leak any information about the model itself? That's what I mean by verifiability and privacy in this context. To give you a brief analogy of how things correspond to in this world, let's consider the Web 2 era, where when in the early days of the internet, we were connecting multiple computers in the network. However, we had no regard for privacy or security. Later, cryptography came up with solutions such as certificate authorities and TLS to make sure that we have some sort of security and privacy. We are at a new interesting crossroads in the AI era, and ZK could be one potential solution, or if not the only solution that could offer both security and privacy. So the branch of cryptography that deals with this problem is ZK-ML, that is at the intersection of verifiable computation, privacy, and machine learning. So it's a new emerging area where you kind of have two key properties that you get from ZK-ML. The first one is efficiency, where you can use in two types of computations. One is in the training, where I can convince you that the model Y is actually trained on some data set R. I don't have to show the data set R explicitly. A commitment to this model is enough. In terms of inference, I can convince a verifier that indeed, if you input a value X to the model, then Y is the correct output that has been computed. In terms of privacy, the one cool feature you can get is like proprietary models don't have to release their weights. Rather, they can just give out a commitment to the model and convince any user that the input-output pairs that go inside this model is indeed correct. There are a bunch of applications that one can envision in terms of privacy and efficiency properties of ZK-ML. Let's explore a few. So in terms of efficient verification, the key properties, the key applications one can think of is, let's say, in the world of inference. Both premium version of ChatGPT and free version is available. Let's say that you are subscribed to the free, premium model. ChatGPT can give out a proof that indeed that the model results which you are getting are from the premium one and not the free one. Similarly, let's say that there is some new benchmark, and ChatGPT out of nowhere claims that they are like 98% accurate or something. It's hard for you to, as a user, to verify this claim. Rather, ChatGPT can compute a small proof that this is indeed the accuracy gain they get. So in terms of training, this also helps to convince someone that the data set that goes inside the training algorithm is actually not copyrighted or something. So let's say when New York Times comes back and says that, hey, did you use my data set? Someone can give a membership proof to argue that this was indeed the case, that you did not use it. And also, it can also help you with fairness-related problems. It can convince regulators that no inputs to this model was discriminated based on any protected attribute. This is particularly useful in terms of, let's say, that a mortgage application or other things that use a lot of personal information. So in terms of privacy, you have two broad privacy categories. One is in the model privacy, and the other one is the data privacy. So in terms of model privacy, as I alluded to before, you just have to commit to the model using some sort of a hiding commitment, and you can compute a proof of inference that this was done correctly. In terms of data privacy, let's say that I want to submit a mortgage application as a user. As I can run approver on the client side based on, let's say, my personal information like bank or social security number, and give out a proof that I'm eligible for a loan. And the underwriter can be convinced that with this proof and the commitment to the model, indeed, whatever I'm giving out is a valid proof of eligibility. So, and all of this is made possible because of ZK SNARKs. SNARKs are succinct non-interactive arguments of knowledge. Essentially, it gives out a small mathematical proof that argues the statement if the trained model parameter is y, and the y is the correct, w, then y is the correct output on input x. Yeah, the key efficiency property that we want from SNARKs are it has to be the proof that comes out has to be really small, and the verifier has to be really fast. And if the proof leaks no information about the model, then it's also particularly zero knowledge. Yeah, there are numerous commercial interests in this space. I don't have to articulate them all, but it's at this point it's well known. So one key thing to notice here is like the prover can send out the entire model as a witness. However, this trivial example of SNARK is neither succinct nor fast because the verifier have to recompute the computation from scratch, and the witness itself is large. So that trivial example doesn't work. So numerous SNARK inventions have led to this moment in time where we can use these systems to build applications such as ZKML. So there are the existing ZKML solutions can be categorized into two broad categories. Ones that are based on high expressivity, and the other ones that are based on high efficiency. What I mean by that is generic solutions like EZKL and so on, they are really expressive in nature. You can pretty much parse many ML models. However, the nature of the tools that are used are very generic in nature. That doesn't have scope for optimization. At the same time, you have specialized solutions from academia. Those solutions are really fast. For example, ZKLLM, ZKCNN, and so on. These books are really fast in practice. But the main obvious drawback is they can only do one specific specialized task. So that's what I mean by low expressivity. So, and of course there are there are tools that are neither expressive nor efficient. So the question which we ask in this work is, can we have a tool that has the best of both worlds? And DPROO aims to solve this problem. So DPROO is a cryptographic library that lets you verify ML inferences. The exact statement that goes about is as follows. Given a commitment to W, where W is the commitment to the weights, Y is indeed the correct output on an input X. So interesting features about DPROO, it's really fast in practice. The prover is at least 2 orders of magnitude faster than the baseline. And the verifier is at least 2 to 8x faster. And on top of that, the one-time setup is also 2 to 3 orders of magnitude faster. Moreover, these can be proved formally that these approaches are in fact correct and secure. The other thing which I want to mention is the key insight that makes these things possible is we use the power of randomness to verify computation rather than compute from scratch. And this stands on top of many years of cryptographic research to achieve these amazing results. So jumping into the architecture of DPROO, so there are roughly like 4 components. The first one is outside DPROO. That's what I call as model training. And after that, it gets inside the world of DPROO, where you have a pre-processing stage, you have a proving stage, and you have a verification stage. To see this in a little bit more detail, let's say that you are some ML model creator. You write your model in, let's say, in Python, Keras, or PyTorch. what you would do is, like, after you train these models, you would export it to the standard format, ONNX format, and along with few sample inputs to the model. So these sample inputs helps us figure out the distribution of the activations that are along the path. So these things are fed as an input to the deepprove library. So where the deepprove parses the ONNX format into graph of operators. Using the sample inputs and so on, it figures out the scaling factors and other related information that you need to make the inference possible. On top of that, you also generate prover and verification keys in this stage. And of course, the prover can also commit to the model at this stage of the pipeline. So currently we support like basic operations like matrix multiplications, generalized matrix multiplications, convolutions, max pool, and quite a bit of activation functions. In the proving stage, the prover first evaluates a model on the input, computes the entire execution trace of this whole graph of operators, and then the prover computes a proof of correct execution of each specific operator. Once you have that, the prover can in fact accumulate these proofs into a single proof that can be verified by the verifier. So when you jump into verification, all the verifier needs is the input and the output from the prover, the commitment to the model, and the verifier keys. And the verifier can in fact figure out if it's correct, accept or reject the proof. So in the rest of the talk, I'm going to use multilayer perceptron as a working example. So this is a very trivial example where I just have one dense layer and one activation function. This should give you a feel for how this works. So what I mean by a dense layer is it's as simple, your inputs come as a vector, and you're going to compute, you have trained your model on some training data set. At the end of this training process, you have a matrix of values. So during inference, all you have to do is take this vector, your input vector, multiply it with this matrix, and that gives out an output. And you use an activation function like ReLU, which essentially returns, if the input values are greater than 0, then it returns the input as is. If it's less than 0, then it returns 0. So it's a combination of these two layers is a very simple, trivial example of how a multi-layer perceptron would work. To make the first part happen in terms of the prover side, you would need, we use the sum check protocol. And to make the ReLU like non-linear functions to make it happen, we use lookup arguments. So in general, the workflow goes as follows. The prover commits to the model. The verifier sends out the input. The prover computes the result. In this case, it's a trivial one. It's just a matrix vector product and ReLU. And then the verifier sources a randomness R1, gives it to the prover. The prover uses this to compute a proof of correctness for the matrix multiplication layer. And the verifier can accept or reject this proof. And the verifier will sample another randomness R2. And the prover gives out the proof of ReLU. The verifier can accept or reject this proof. So I'm showing this just as an illustration. The actual protocol we have is non-interactive, so you don't have so many rounds of interaction going on. It's just one shot proof that comes from the prover based on the commitments and so on, based on random oracle assumptions. So this is slightly getting into the technical weeds. Essentially, sum check protocol is a seminal work from the 90s. The prover has a polynomial, and it's trying to convince a verifier that the evaluation of this polynomial on a Boolean hypercube is some specific value y that looks like the Scadi equation. We don't have to know the details of it, but essentially the key efficiency which we get is the prover can compute the proof of this function in near linear time, and the verifier's work just depends only on the number of polynomial time in the variables. So in the dense layer, you have a known matrix W. That's essentially the weights of the model. Then you have the input X that comes in as a commitment to the verifier, but the prover knows this in plain text, and you also have the claimed value y. That's going to be the output. So using these, prover holds the x, y, and w, and the verifier has the commitments and the output, and one can invoke the sum check protocol here to convince that this is indeed the correct. So I'm going to skip a few details in the interest of time. Essentially, the key thing that you need to make it happen is like you need to convert these matrices into multilinear polynomials, and that lets you run the sum check protocol. So this is where to prove the dense layer, the verifier will sample a randomness and gives it to the prover, and the prover in some essence invokes the sum check protocol in this manner. I know this is a bunch of equations, but believe me that it works. And this is useful to perform many linear operations, such as convolutions. Then you can perform Hartman product, transpose, and a whole suite of operations which frequently occur in machine learning. The other key ingredient is the lookup arguments. So years of research have gone into building great lookup arguments. Essentially, you don't have to compute a result. You just have to prove that it's inside a table. I know that I'm rushing right now, but these amazing cryptographic techniques let you prove nonlinear arguments. That's, if you want to take away anything about lookup arguments and how it's used in deep proof, that's all you need to know. And you have to you can look up a result rather than compute it. So in this case, you can do ReLU in this manner where you have an input column and an output column, and all the prover has to do is to convince that whenever a value comes in here, it belongs to this table. So when we benchmark this, we see the prover to be at least 2 orders of magnitude faster, and the setup is 2 to 3 orders of magnitude faster than a baseline. I don't want to bore you with more of benchmarking details. After we released our code on GitHub, there are others who ran benchmarks, and you can go see their own. You can see they're run by independent parties. You can see the benchmark results from them to corroborate what I'm saying on the slide. So the only drawback is like we have a slightly larger proof size, but that shouldn't be a problem if you're especially doing a recursive composition using ROT16 or something. So overall, the key optimizations are like we use great commitment schemes, use the power of randomness, and we use properties of FFTs and so on to make convolutions happen, and we use lookup arguments, quantization to make this happen. So with this, I'll stop and take questions.
Any questions? Okay.
Since sum check is based on finite fields and LLMs work with floats, how do you?
So you need to. I didn't go over that. Yeah, essentially, you need to quantize your model to some reasonable value.
Okay, fair enough.
I was wondering, does it had some compute time, or I was wondering about the added compute time.
You mean concrete computation time?
Yeah, due to the verification.
So
compared to without verification.
So this is up to 2x faster, but in terms of prover time, there are models where you can do it in under 1 second. And off the top, I don't remember the verification times, but they're at least 2x faster. Yeah.
Yeah, and whatever the size of the model.
It's not fully linear. It depends on, it grows in polynomial in the number of variables. So it's not a constant verification, but there's a log component to it, yes.
Thank you. No more question?
Variables. The variables of the sum check. It doesn't have like in the size of the model? No, the log.
So probably the last question.
So just out of curiosity, did you try or could you prove some bigger models, like if you took the Olama, DeepSeek, or whatever?
We're actually working on that. So we are expecting a next major announcement to support those models.
Awesome, thanks.
Thank you very much. We can thank the speaker.